Hello friends, welcome to this session of Learning R, and in this session we are going to learn the different steps in model fitting using Caret package. And Caret package is very useful package, a comprehensive package which provides us functions for model fitting and for various different steps in model fitting. And those steps are, the first step is we will use here that loading required libraries, and these libraries are the Caret library, which will provide us model fitting function, then read Excel library, which will help us to read the Excel file, which is our data input file, that is resin data set, and then we'll go for the pre-processing of data. But here we are using a clean data, therefore much pre-processing is not required. Only the pre-processing we do here is we will convert the class variable of our data set into a factor variable, because it is a character variable, and converting it to a factor variable will is required to fit the model to that. Then we'll split the data into training and testing data, and that is required because while predicting from the model, we should use the data which is not used for fitting the model. If we use the data seen by the model for prediction or for validation of the model, then that overfitting or those aspects cannot be seen. And for that purpose, we need to use the data which is not seen during the model fitting for validation of the model. And for that purpose, we'll split the data into training and testing data. Then we'll set up the cross validation rules, how to cross validate that, how many iterations will be used for that, how many times the model will be fitted to the trained data, to the subsamples of the trained data, and then the model will be validated and the best model will be used further. Then define hyperparameter tuning grid. These hyperparameters here are different according to different models, and as here we are using the random forest model for fitting classification model to the resin data. These hyperparameters are MTRY, and that MTRY, if you want to know more, then we need I need to make a different video to explain MTR. The MTR is the minimum number of variables which are used in each step, and for that a different video will be required. Then after these 6 steps, actually this is the 7th step, is the we are training the model. Actually there we are using the model formula and in the train function, and will fit that. Then 8th step is there where we will evaluate the model performance by predicting for the test data, and by looking at the confusion matrix where the model is getting confused to predict the different classes of that data set. And then at last step we will study the variable importance, and this is the variable importance chart, and that we can see here that perimeter and measure axis, these 2 variables are highly important. We can use this variable importance chart or plot to reduce down number of variables which are being used for the model fitting purpose, because higher number of the variables used for model fitting means more computation is required, and that model becomes computationally very costly. And if your observations which are being used for training or testing are very large in number, and variables are also very large in number, then you will require very high capacity computers and very high computational power, high energy also to fit the model. And for that purpose, less number of variables are very useful, and for that we can go on minimizing the number of variables to get the satisfactory performance of the model. And that's all about introduction of the model. Now we are there at the actual model fitting process, and for that purpose, load the library Caret to get Caret functions in memory. I will run that, and if you get any error here that package Caret not found, then you can go to tools and install packages, and then when the dialog box opens, you can type there the name of the package and click install Caret, and this Caret select from the drop down list and click install. Package will get installed. And you can do the same for this read Excel also, and for random forest library also. And this library read Excel is required for reading Excel files, because our input data is Excel file. Then library random forest is there. This random forest library will be used at the backend of the Caret to get the random forest algorithm to fit the random forest model. And as an example, we are using that random forest here model here, and I have set the working directory. You don't have to set working directory if you or don't bother where your output will go or from where your input will come. But setting working directory is quite handy. It's little tedious, but I will show you, I will demonstrate you again here how to set working directory. Set working directory function is there, and you have to put that path in inverted code. This is the path, and how to get this path. I will go to Explorer, this is folder view, and this is my directory where my data file is there. This is my data file, and this is path of that directory. I will click here in the path, and then the path gets selected. I copy the path, Control C, and bring that path here in this setwd function. And this backslash is actually used in R as escape sequence. Therefore, we will make that, we'll escape that escape sequence itself by using that double backslash. And now this will be read as /rworks. This will be read as /model. Model fitting using, and I will run that. Now working directory has got set, and you can see here that working directory is there. Now I will just remove that because it's a double code. Then this read xlsx function is coming from readxl package, and this package will take name of the file. This is again the path, but we have given the path here. We have set the working directory. Therefore, this entire path is not required. We are just providing here the relative path, means the file name here. And that file name, I will go here in the folder, copy that, or right click that and rename. And then I can copy this name. I bring that name here, and in that I can paste this name along with its extension. And when I run that, that data will get imported, and here you can see the data. Data has got imported, and we can see the structure of the data to know more about the variables. And here if you see that area variable is there, it's a numeric variable. Major axis length variable is there, it's a numeric variable. Minor axis length is numeric. Eccentricity, convex area, all these are parameters of resins. Resins are dried grapes, and these two varieties are there of the resins. Classes of resins are there. One is Casemen and other is it's not shown here. If you want to see those different resins, that I will use this unique function, and in unique function data $class class is here, and when I run that, you can see that these two values are getting repeated in this class, and the first value is Casemen for many, and then followed by Besni. Okay, these two resin varieties are there, and we are using this model fitting to predict the variety based on these different parameters. Okay, when we measure the parameter, when we get the resin, we'll measure the parameter, and we can identify whether that is Casemen or Besni. This is the purpose of that model. And now I'll just run this as dot factor function, because here it's a character variable that can also be used, but when we convert that to factor variable, that will be more useful. Therefore, using this as dot factor function, I am converting this data class variable of this data to factor. I will run that, and now we'll see the structure again. For this purpose, I will copy this function here, str data. I'll run that, and you can see now here that class was character, and now here that class has become factor. Now with two levels, that Besni and Casemen, and now instead of showing it as character in the data, it is storing that as number. That Casemen is the second level, and Besni is the first level. This level arrangement by default is the alphabetic arrangement. Now we have pre-processed the data, and now we'll split the data into training and testing data, and here that we set the seed as 1, 2, 3. This set.seed is required to ensure reproducibility of that random number generation, because that randomization process is here in getting these training indices also, because these training indices are the row numbers of the data which will be sampled. And for that all the random events here to ensure reproducibility in the next session, not in total reproducibility will be there, but a fair degree of reproducibility will be there if we set the random number generation, that seed 1, 2, 3 seed here. You can use your own number also, 6, 4, 5, but ensure that when you try again next time, this seed must be the same, so that you will get the reproducible results. And this training indices are the indices of the rows which we want in training data. To get those, we will have to sample this data, and here we are using this data $class, as the y variable for this create data partition function. And when I take cursor, you can see in yellow box that first variable is y. First input is y for that create data partition function. And here data class is the categorical variable, a factor variable, and there stratified sampling will be done. That create data partition selects the sampling method based on our output dependent variable which we are using for model fitting purpose. And this create data partition function, I click on this, then I go to the yellow box, and from that yellow tooltip help I can put the arguments there. And the first argument is y, that is data dollar class. Second argument is times. We are not using time here, we are using this probability 0.8, means in training data 80% of the rows will be there, and in testing data 20% of the rows will be there. And by default that output is in the form of list. We don't want list, therefore we have made that list is equal to false. We'll get matrix output of this training indices. I will run that. And by using this is.matrix function, I'm showing you whether it's a matrix or not. I will run that, and it is saying that it's a matrix. I will show you this training indices also, and you can see how it is getting printed. That head should have been used because 80% of the 900 rows are there, means 720 rows are there, and this is the row number, and after that all columns we need, and this only one column is there, and therefore we are seeing this column, and this column name is training indices. And that deemed training will see that 720 rows are there. 720 out of 900 means 80% of the rows will be there, are there, have been selected. If you see here 879, 880, 881, 882, 83, 84, 5, 6, 7, 8, then 89 and 90 rows are not there. But those rows will be there in the training data. In the testing data, these rows we will use for the training data, and this training data set contain data index, this square bracket we are specifying indices, training indices, comma, and this one here, this 720 rows will be used, will be selected as the training set, and remaining using this -1 in testing data, we are using this index matrix as the -1, -1 means we don't want these indices, we want indices other than the training indices which will be there in the testing data. I will run that, and we'll see training data set. I should have used the head function, but it's a table. It is showing me the first few rows only, because this data we read using the read Excel function, therefore a table output is there, and this create partition, this selection is also providing us this table output. In testing data also I will run that table output will be there. I will run that, and this table output is there, and when we see the dim of testing set, that will be 180, means 180 rows are there in the testing data, 720 rows are there in the training data, and that training data we are going to use for training. I am repeating that many times. And now we are through with the splitting the data, or splitting data step is over, and now we are there at the setting up cross validation rules. And cross validation is required to validate our model and to select for the best fitting model. And for that purpose, at each step that cross validation will be done, and best fit model will be used further in the iteration. And for that train control, we are using method cross validation CV. Then 10 iterations will be there, means our test data will be broken down, input data will be broken down into 10 different subsets, and on each subset the model will be fitted, and its model fitting performance will be evaluated, and best model will be selected for that. Save predictions, the only final model will be saved there. Class probabilities will be calculated and will be stored in the model object, and summary function will be 2 class summary, and that summary function will be used for binary classification, though to ensure how those classification is done in that 2 categories, that Caesimen and Benzini. Then tune grid is there. This is for hyperparameter tuning, and here as I said that in random forest hyperparameter is MTRY, and for that I need to make a different video to explain what MTRY is there. But here just remember that MTRY is the minimum number of variables used to fit the model at each iteration, and here we are using that as 2, 4 and 6, and this grid will be used in the train function to get the best fitted model. And now this train function is there. I am saving the fitted model object with the name model. Okay, my model object, trained model will be there as the model object. Name model will be there. This train class, then this tilde symbol to this is the symbol for formula interface, and class is the dependent variable, and followed by, when dot is there, this dot is the shortcut to use all other variables other than class variables which are there in the data. And I am giving all the variables in this formula. All these variables will be used as dependent variable: area plus major axis length plus minor axis length plus eccentricity plus convex area plus extent plus perimeter, and this class is the our dependent variable. All these are independent variable or IVs. Then data will be training data set. Method is random forest. I am specifying that method here. And train control is the train control. That train control object we have defined here. Then tune hyperparameter tuning, that tune grid is also there. That tune grid we have defined here. And this model I will run. It will take some time because many variables are there, 900 rows are there, and my processor is not that much strong. That sorry, I selected this O and press the control enter, or ran the model. I will run that model again, and this will take little time because at the back end much computations are required. Many decision trees will be prepared, and out of those decision trees it is saying that the accuracy was not in the result set. ROC will be used instead. Okay, let's ignore this warning because we have got the model fitted model, and no this warning message is not that much important also for us too. And then after this model we can see the model. I will run that model to see what is there in the model. It's a random forest model, 720 samples, because 720 rows were there, observations were there in the training data. Then 7 predictor variables are there, and one dependent variable was there. Predictor variables means independent variables, and 2 classes were there in the output. One is Besney and other is K-Siemens, and we are using this model to classify our data either into Besney or either into K-Siemens. The non-pre-processing is there. Resampling, cross-validated, 10-fold cross-validation has been done, means 10 subsets were done and model was fitted. Summary of sample sizes in those all those 10 subsets, 648 was the sample size used to fit the model. Resampling results across that one. For MTRY2, ROC was 0.92. This is the performance matrix and it's quite good. Sensitivity is 0.83, specificity is 0.89. This model is performing better. A good model it is. ROC was used to select the optimal model using the largest value, and the final value used for the model was MTRI4, because this MTRI4 is giving the better values in terms of sensitivity and in terms of ROC also. And therefore this model with MTRY or 4 variables will be used further. And now then variable importance is there. We are calculating, and this variable importance will be calculated using that var imp function, and model will be the first one. This is that model will be the object, and scale we are using as true. That scaling of the variables will be done to get the accurate values, because some variables tend to be very large in magnitude, some variables tend to be very small in magnitude, and if you don't scale, then our results may be skewed towards the larger variables. We are scaling here, therefore the skew will not be there. And this importance, we'll see how it looks like, variable importance, and these variable importance are there. Perimeter is the maximum, 100 importance value is there. Major axis length is 84. importance, convex area 26, eccentricity, these two variables. The single variable can also give us a good model. Okay, I will not do that submodeling, but if you model that using, instead of using this here dot, you can replace that dot with perimeter, only perimeter, and fit the model and find out the model performance values. And if this only with perimeter model is better, then you can use that also, because only one variable will make that model very cheaper in terms of computational cost and computational complexity. Okay. Let it be. That variable importance we can plot as a bar plot also, but that bar plot, this will be the input. Plotting that using the bar plot function is little complicated, and we are not getting the satisfactory plot also. Therefore, just ignore this line of code. I am putting that as comment, and here you can use this plot method, generic plot method on this importance object. Okay, this importance object we calculated here, and that main title will be variable importance plot. And why that plot function, generic plot function, is giving a plot similar, giving a plot like this, is because this object is little different than the simple data frame. This object will see the attributes of this, and you can see here that class of this object is var imp train, and the plot method defined in Caret for this var imp dot train class is this one. We are getting a segment or lollipop chart, and again the flipped chart it is there. Numeric variable is on x-axis, this is the importance, and on y-axis to ensure that these names are shown correctly, because in x-axis those names will overlap with each other, or we may have to change the orientation of these names, and that changed orientation, if you make that those vertical, then it's very difficult to read. This chart looks good, and simple bar chart is not sufficient. Therefore, this plot method they have provided in the provided for this varimp object in the Caret function. And now we'll print the model again. We have seen the model earlier, but I am running this again to show you the output of the print model. And now we are going to the confusion matrix. In confusion matrix, we actually compare the predicted values, and here to predict values we are using predict function inside the confusion matrix, this predict function, and predict function takes first argument as the model, and then testing data. Testing data, 20% data we kept, which is not seen by the model during fitting. That model we are using as the testing to see the confusion matrix, and this is the actual value. Class is the actual value in the testing data set, and this first column is the predicted values, and we'll run that confusion matrix to see the confusion matrix. And you can see here accuracy is 0.8056, and that model, I'll again confirm whether that model is there. Yes, model only. Then that accuracy is 0.8056, quite less accuracy it is, but it may be satisfactory. 0.611 kappa. Kappa value is the ratio of the actual probability of proper prediction and the other probabilities by chance prediction divided by 1 minus chance prediction. We'll make the another video to explain the kappa. That p-value of actual, that not p-value to accuracy is greater than no information rate. No information rate means model which is predicting the most common class. It's a usual observation. If red balls are more in your bag, and if I ask you to blindly pick up a ball and predict which ball it will be, red or other color. If red is most common class, then by intuition you can predict that it's red, and probability of getting red will be higher. That's called as no information rate. A no model will predict this no information rate. But here accuracy is greater than this no information rate. Accuracy is greater than that by chance prediction, and that probability is 2 multiplied by 10 raised to minus 16. Therefore, quite less. Therefore, our accuracy is greater than the no information rate. that we are accepting. Then McNemar's test p-value is there, and this p-value is 0.73, means our model is performing better. And sensitivity values, specificity values, and all those are there. If you go on, here below I have reduced the model many a times. First perimeter is there, the best one. We can run that and we can find out the confusion matrix to see whether prediction is getting improved or not. And we can keep on eliminating or go on adding one variable each time to get the maximum prediction. Okay, that's to get the best possible model. And here the trend function has provided us this model which is predicting 80% time it is accurate. Here for Besney, 71 correct values are there, and Besney resins got confused for K-Simon 16 times, and for K-Simon 19 times it got confused and classified that as Besney, but 74 times it predicted that K-Simon correctly. Means the model is fairly better in terms of its predictive ability, prediction accuracy. That's all in this model. We have seen how to load required libraries, how to read data, then how to pre-process data, then splitting data into training and testing sets, very important process in model fitting. We have seen that also. Then we have set up the cross validation, again another important step in model fitting, model training. Then we have defined the hyperparameter tuning grid. These two arguments will be provided to the train function. We have trained the model using random forest approach, using the train function of Caret package. And then after training the model, we have evaluated the model performance by using testing data set and using the confusion matrix. And then we have studied the variable importance also. And as optional, if you want to, you can fit the model to different combinations of these variables and see which combination is giving you the best results. And that's all for this session of model fitting. Please click the like button that you like my video, and if you have not subscribed to my channel, please subscribe to my channel. Please share this with your friends also. And thanks for watching this video.